So welcome back, everyone. It is my great pleasure to virtually welcome to the Cardiff Analysis Seminar Tuomas Sahlsten from the University of Manchester, who will talk about quantum chaos on random surfaces. So Tuomas, the floor is yours.
Okay, thanks, Matteo. And I hope you can hear me now at the moment. And if there is a problem, they have promised a power cut in my area within the next 2 hours. So let's hope it doesn't happen in the next hour. If it does, then just wait a few minutes and I'll use my mobile internet. Okay, so this topic is something that we've been working on for a couple of years, and we are currently exploring some further directions in here. And I just want to give you a little bit of maybe a taste of this topic, where it kind of combines ideas from graph theory, random graph theory, and also surfaces like hyperbolic surfaces or more general negatively curved surfaces. And we are kind of like getting some type of theory connecting these some of the ideas from the other one. And the topic here is this notion of quantum chaos. So let me give you a brief introduction to this topic. So one of the key problems in the field is this quantum unique ergodicity idea of delocalization of eigenfunctions of the Laplacian on negatively curved surfaces. So let's take just a compact negatively curved surface, so no funnels or anything, just really compact surface. And here, because the compact surface, you have a discrete set of eigenvalues. I denote lambda 0 as the zero, like this, and then the lambda 1, there's a gap between those values because of the negative curvature. Okay, this would be a hyperbolic surface, for example. You could have this kind of thing example. And then once you have eigenvalues of the Laplacian on the surface, I kind of assume that maybe most of the people in the audience know what is the Laplacian on a surface, at least maybe heuristically. Then let's take an orthonormal basis corresponding eigenfunctions and normalize them in L2 just for fun. And then there are two conjectures which are still open. If you take a continuous test function on the surface X, let's say I just take it in space, so just in X, no phase space here. And you take these averages over the space, so test it with this L2 normalized function. So it's a probability measure. You could think about this psi lambda j x squared as a probability measure with respect to the volume on the area, whatever you want to use in the surface. And then you have a test function. You hope that this to converge to the volume, one of the volume, because this is the normalized volume of the surface. So that it should behave like this. The other conjecture, which is related, it's kind of to do more with the delocalization, that not too many extreme values, that there is a decay in the L infinity norm. This is a conjecture that if you just take the eigenvalue lambda j and its L infinity norm, and you can bound this by some, if you fix an epsilon, then the growth of the L infinity norm is rough at most this, so it can be as small as possible. I think there's a survey by Peter Sarnak which has these conjectures in this form. I'm not sure how to there probably are better references, other places where you can find these conjectures. This is kind of like the motivation, and I don't think there exist any examples. So there are some papers in like number theory, more arithmetic number theory, where if you take a special orthonormal basis of the eigenfunctions of the Laplacian, which is called a Hecke basis in certain, so let's call them like congruence covers of modular surface, that would be a non-compact example, but there are some like also compact examples, like these kind of arithmetic surfaces. There you can prove this conjecture, this, for example, the quantum unique ergodicity. But even there, it's not completely known. So it's not known whether that's the only basis. So if you have other like multiplicity in the terms of the eigenfunctions, then you might have other bases. So this is still open in every surface. So this is not known. So the kind of hope maybe motivated by the kind of Erdős's idea of like going into random graph theory. If you want to find a counterexample to something or prove something is true, then maybe prove it for almost surely, like almost every something satisfies the conjecture. So even finding one example would be interesting. So that's why I'm like thinking if there's a random model, what you can do. So let's see where we can get with this. So if there's a random model where, for example, one of these conjectures is true, that would be very interesting. That would be possible. So let's start from somewhere where we can do some random models and where things some conjectures actually are true of this type. So I call about these deregular graphs where you have a fixed degree and every vertex has exactly d edges connecting into it. And you can define a Laplacian here. I call this the Laplacian. There are other maybe definitions I've seen using the adjacency matrix. So this is kind of one definition I've seen, which just you take the points on the vertices and you take all the neighboring points. So this notation just means you're connecting. So there's an edge between the points, and then you subtract the value of the function at the point x and divide by the degree. So this is like a differential operator you can define. Okay, and in the set of all random graphs, there are several models. There's like, for example, there's something called switching model. There's something called permutation model, and also the uniform probability model. They are different types. There are some advantages in spectral theoretically, and probabilistically, there are some advantages using different types of models. So let me just define one of the models, which is the uniform probability model, where you just take the uniform measure in the space of all deregular graphs of degree d, and a vertex size is n. It's just a uniform measure on the space of graph. So that's a model, a random graph. When we go to surfaces, you will see that it's not as simple to define these random models, but here is quite easy. And then let's take the set of all L2 normalized eigenfunctions of the graph. Just this notation I'll be using just to simplify a little bit. Then there's a theorem of Bauer, Schmidt, Knowles, and Yao from 2017. Actually, it was, I think, earlier already on archive, where they take a random irregular graph. Let's say with this model, they have other notions of random models as well, where this holds. And they take any L2 normalized eigenfunction on the graph. So you can take that, again, eigenfunctions of the Laplacian. Then they prove this kind of L infinity upper bound. So the L infinity norm of the eigenfunction is bounded from above by, okay, there's some fluctuation terms. There's some like fluctuation happening, which gives you this logarithmic growth on the top. And then they have square root of n here. And this happens with probability at least 1 minus e to the power minus 2 log n to the power 3. As long as the degree is at least log n to the power 4. Okay. So you need to assume the degree is growing at the same time as the n is growing. So in some sense, you're changing your graph. You're making them bigger and bigger all the time to be able to make this happen. And here, I'm saying this is kind of like an optimal theorem in the sense that if you take the uniform function on the graph in terms of L2 norm, that it has L2 norm 1, like L2 normalized to be 1, then it's 1 over the square root of n on each vertex, that function. And that has L infinity norm 1 over square root of n, of course, but by definition. So that's kind of the most uniform function on the graph of n vertices. And this is just saying that this is the best possible bound you can get. So you can get to all of these functions, actually, this kind of a bound, almost like the uniform bound in a sense. So this is like the kind of the analog of the conjecture that was in the quantum inequality with the bound for the eigenvalue. But here we are not talking about eigenvalue. This is just depending on the number of vertices. The problem with the graph is, like you can probably guess it, that the spectrum of the Laplacian is finite set. So we can't really go to infinity. So we have to figure out some other way to go to infinity here. So what we do here in the graph is just taking the number of vertices, for example, infinity. Here with this theorem, what they prove that they also take the degree to infinity. So the number of like edges to a given point start to grow as well at the same time. There is some meaning to that notion as well, which I'll come back to later on when I talk about the surfaces. There's some connection here that we like to maybe explore. Is this okay? I'm leaving this as a kind of statement. This is kind of the main motivation for what we are doing. Okay. If there's any questions, just put it on the chat or something. I can see the chat in front of me, so I can answer those immediately. So the surfaces, let's try to go. Can we kind of go into this quantum unique-periodicity, for example? Does it help at all? Like, does this help with these questions? So first of all, we need to understand what this means to be the large cardinality. Remember the n in the previous theorem was the number of vertices. So the number of vertices, you can kind of connect it to the idea that your surface is like a large area. Like if it's a two-dimensional surface, it's getting bigger. That's how I would see the large vertices, for example. It's just a bigger area in the surface. So it's not to do with the eigenvalue, really. It's just a topological geometric notion. So the kind of what people have studied as an analog of this kind of, let's call it like a quantum unique-periodicity in terms of like large area, for example, is this level aspect theory for the this is type of like let's call them these mass forms, for example. So if you get lost at this slide, just be okay. Just you don't even need to read this slide. But basically, this is just saying that there are some papers that you can actually prove this type of similar types of theorems as on the graphs that I just shown in the surfaces. Where you bound actually, if you look at this, for example, these examples, I'm taking this, these are very standard example of an arithmetic surface. And this is actually a non-compact example because this was the easiest to write. I could have brought, there's also a compact version of this theorem by Saha, but it's also a bit more difficult to write down the assumptions and everything. So I brought this example of, this is called a congruence cover of the modular surface with the level n. So this n here that you see inside here is the level. So it's to do with this like congruence relation that you have here. And if you now take an L2 normalized, something called Hecke mass cuspidal new form, don't ask me what it is. I have some idea what it is, but let's leave that to later on. But this is it's an eigenfunction of the Laplacian. That's the important thing. But it's a certain property, certain like symmetric properties on it, which you don't have for necessary for eigenfunctions. And then you can bound this by the volume. You get the volume of the surface to the power minus 1/12 plus epsilon. So this kind of looks like what happened before, but the exponent is 1/12, so it's not the half that it was before. So there is something like this, and that's why there's like a conjecture actually in the field, which I'll come back to later. That would be like half here. That would be the like natural conjecture. But you can see that this is not really helping with the eigenvalue. You're just taking eigenvalue here, like that's constant. So the constant in eigenvalue would be absolutely horrible. Like if you go to the semi-classical limit somehow, then that would be a really possibly a very bad estimate. But let's just see what to get from this. So this is kind of like what's the arithmetic version. Okay, I think I moved this actually. Yeah. So what's the kind of then the analog? So I guess it doesn't want me. Yeah. So I'll give you a theorem that's it's actually we proved this already a couple of years ago, where we proved some type of quantum ergodicity type of a result, which gives you like a bit like not exactly quantum unique ergodicity, but it's kind of like an averaged version of that result. So so we take a compact hyperbolic surface now. So hyperbolic surface would just have the negative curvature -1 everywhere. So it has a homogeneous structure, which gives advantages in the theory, some advantages later on, but I'm not sure if they are absolutely necessary in this theorem. But anyway, so let's take the eigenvalues of the Laplacian. And denote that they depend on x, because the x is kind of varying here, the x is changing. And I also take the orthonormal basis of the eigenfunction of the Laplacian with these eigenvalues as before. I've just emphasized that they depend on x as well. And then I introduce a couple of geometric parameters. One of them is the injectivity radius. Those who know something about hyperbolic surfaces, then a hyperbolic surface can be obtained as a quotient over this kind of what do you call it, like a polygon or something on the a hyperbolic plane, and by quotienting them out at the it's a bit like how you create like a torus with several holes. You obtain by this like gluing like edges together according to a group that's acting on the plane, a discrete group acting on the plane. So the injectivity radius here is just the largest possible ball you can fit inside the fundamental domain that's isometric to the whole plane, to a ball in the hyperbolic plane. So it's kind of like saying how much of the surface looks like the hyperbolic plane. That's kind of like a portion. Like when you take it too large, the ball that you put inside, it can wrap around a bit too much, and that's no longer isometric to a ball in the hyperbolic plane. It's kind of a measure of size, basically. So we take e to the power injectivity radius, kind of get roughly like a volume of the surface, or the area of the surface, roughly. And the other notion I use is this thin part of the surface, which is like the points where the injectivity radius is less than r. So there are some parts of the surface which are like a bit tangled, like there's a lot of twistness going on. So you can't really fit a big ball there. It starts to wrap around actually after like making slightly too big. So it's like given an r, we can always find the part of the surface which is like the thin part of the surface. If r is huge, then of course, like you can't really, this is so easy to like find the whole points of the surface satisfy this condition. But if r is very small, this can be actually a very small set, can be empty possibly. And then we prove this bound, a quantitative estimate on this thing. So I'll take a test function of integral 0. So I'm subtracting the mean. So I'm just like test function integral 0. I take a compact subinterval of the spec. Basically, this could be considered the spectrum. So I take from 1/4. I start from there to infinity, and I take that given this interval in the spectrum, there exists an Ri such that for any r bigger than Ri, and for every a, which is this test function, bounded test function with integral 0, I can bound this if I sum over the whole eigenvalues that are inside this interval I. So remember the quantum unique ergodicity was considering without this summing here. So I'm actually summing over all these points, and then I get this bound from above by the volume of the surface. Then something that depends on the spectral gap. There's a continuous function that kind of depends on the first eigenvalue of the x. There's an r, this is the r that I fix here. For every r bigger than ri, I have this r here. And then there's e to the power 2r volume of the thin part. I'm using the volume like, because it's like this could be in higher dimensions as well. We could prove this kind of theorem as well. So it's like a volume of the thin part and the injectivity radius. And then you have the L infinity norm of the two. Okay, so it's an extremely quantitative estimate, but the right-hand side only depends on pure geometric quantities. And you can exploit this estimate to make something useful happen. So, so it looks a bit technical. There's not there's a lot of parameters here going on. But then the idea here is that once you sum over here, you sum over these numbers on the left-hand side. And then if you divide by their number, that means you need to divide the right-hand side by their number as well. But it turns out that there is some kind of like a Weil law going on that you can possibly bound that roughly by the volume. So you kind of actually can make this estimate something that measures like on average these quantities on the left-hand side, which are in the quantum unique ergodicity question, they will decay possibly. So I'm showing this theorem in the next slides. So you will see what I actually mean by this. But this is a very important estimate because this allows us to transfer to the random surfaces now. So let's talk about the random surfaces. So I'm going to model a model of random surfaces where you can make these estimates that I just had on the previous slide an effective estimate somehow that you can get something useful out of it. So there are several models of random surfaces that now exist in the literature. I'm concentrating on this Weil-Petersson model that Maria Mirzakhani was using in her work a lot, because it has some like pleasant features, like there's something called the integration formula. for this random surface model, which we exploit heavily to get very nice and good estimates from here. That's why we chose this model. But there are other models which are more combinatorial, and maybe some models that might be close to like graph theoretic ideas, which are maybe also good, like they turn out to be good. But let's just talk about this model. This is somehow the one we consider. So if you're not too familiar with moduli spaces, then this might be a bit like, again, just stop listening or something. Just leave this as a model of random surfaces with certain nice properties. But let me very briefly give you an introduction to the model. So we have the moduli spaces of compact hyperbolic surfaces of genus G. This is basically something that you define using topology of the surface. You start from like a topological surface, and you put there, like you try to like put like a space of all the possible metrics in the surface that are hyperbolic. So there are like on this genus G surface, which has several number of holes, let's say a fixed topological surface, then you can fix several different types of metrics on the surface. So you can think about the moduli space somehow like giving you this kind of like a collection of metrics, but they have certain like properties that like identify them with each other, like certain properties that like homotopically they have to be the same type of surface. So let me just leave this for now like that, but there's an intuition which I will come back to in a second to define that a bit more carefully. And in this moduli space, there is some probability measure which is coming from something called Weil-Petersson volume. That's a natural probability measure that comes from the how do you define the moduli space using something called Teichmüller space, and Teichmüller space is a natural volume form that you can then use to define in this moduli space. And let's give you the rough idea what this Weil-Petersson volume is. So we fix a surface of genus G. So this could be like, let's say, we could be a topological surface, but let's say here a hyperbolic surface of genus G. And then what we can do is that once we fix this surface, we can create loads of other surfaces by cutting this surface open, or to create these collections of something called pairs of pans that look like this in the picture. So we take this surface of genus G and cut it open, okay? And then we like scale them a little bit, the surface, like we stretch the ends of the pans to make them squeeze them out a little bit more to create different lengths. So these are these Li components where we create different lengths. And then we also re-glue them back together on top of each other with certain twists. So we can twist the surfaces on top of each other just a little bit. And if we go over 2 pi, then we have to like basically identify those actions. And so that's kind of roughly what the Weil-Petersson volume is. It's basically the normalized Lebesgue measure on the space of R plus 3G minus 1 times 3G minus 1, where this is the number of lengths that you get from cutting the surface open, stretching them and re-gluing them back with some twist going on. So the geodesics can kind of twist around a little bit. They can do these weird properties. And that's how you create the random surfaces. It's basically coming from the Lebesgue measure and we're using all these modular space actions that do make it happen. Okay, that's very roughly what Weil-Petersson probability measure is. I think that's enough to know about this. I'm gonna leave it for now. You can read about the exact definition in the literature. You might get a more idea what's actually going on. And then what the reason I want to talk about is this theorem of Mirzakhani, which was recently actually generalized by Laura Monk, who's a student of Nalini Anantharaman, and she managed to they managed to prove this, that if you take the set of all surfaces of genus G, so this is now inside the moduli space, you do some identification of the surfaces, you use the moduli space notation, that it's like a collection of an element in AG is basically a set of surfaces with certain like identification properties going on. But then you think about them as like a random surface, and then a set of all these surfaces with this thin part. Remember, we had in the previous the quantum Hercules bound that we had is bounded by this kind of quantity, and you assume that the injective radius of the surface has this property, that the injective radius is bounded from below by g to the power -1/24 and log g this, and then you assume the spectral gap is bounded from below by a constant, which is log2 of pi plus log2 squared times 1/4. You just take this set of surfaces with all these three properties that is simultaneously satisfied. Then the Weil-Petersson probability goes to 1 as genus grows to infinity. There's even a rate to this probability growth. Actually, you can say how fast does it grow, but basically it goes to 1 when the genus starts growing in this surface. That's the kind of main results that they had. And the other result that is actually very important for the spectral side of the thing is this result of Monk as well, where she proved that if you take the number of eigenvalues in an interval, remember we had this interval I previously, you take a compact interval, then the number of eigenvalues inside the interval divided by the volume actually is roughly a constant plus an error term that decays when the genus grows. You can see this is actually a decaying error term. So there's just something that only depends on the interval I. When you fix an interval, then there's a dependency of this type. So that's saying that actually, if you now put all those together, what are these three things, what I did with Etienne Le Masson, and then putting these papers of Mirzakhani and Monk, you get this kind of quantum ergodicity for random surfaces. So if you take an interval, which is a compact interval, and then for a random surface in this Weil-Petersson model, the probability that for any A with, okay, test function integral 0, we have that the averages over these quantities decay. So think about like, if you're testing basically how close it is to an integral 0 function. That's kind of what the quantum ergodicity. If you prove quantum unique ergodicity, for example, you test the test function with integral 0, and then you prove that these quantities also decay to 0 at the same time. So then you prove it for all those test functions. So this is like an average version of this, and there's a rate given by a log genus that comes out of the kind of estimates that they have. And there's even a rate to the probability. Actually, you can get a rate at which this convergence happens. Okay. So that's kind of like the theorem that you can get from here. There is a quantum ergodicity in the large eigenvalue limit as well. This is the kind of very classical work of Colin de Verdier and Steve Cheldis and sorry, I know who was the other guy? Sorry, this is very embarrassing. I forgot the name. Colin de Verdier. He's the guy who actually did the original physical. Schnirelmann, yes, that's the how. I think I'm not sure if I pronounced it correctly, but Schnirelmann is the first one. So they have the same type of a result of this type for large eigenvalue. So this is kind of like a version of that for large genus, which is kind of like large volume. So, but then we also studied the L-infinity norms. Remember, this was the other conjecture, the delocalization question. So we also proved recently this kind of a very geometric estimate for the L-infinity norms, which resembles of what we had for the these test functions. So what we take is this this kind of number. So what is this here? This kind of technical number. So we define this kind of a number for any surface x that we define a number Rx and Cx to be any numbers that satisfy this property, that for any delta and for any C delta positive, there exists a C delta positive, such that the supremum over all the points, pairs of points in the fundamental domain of the surface have this property that the distance, and then if we add this gamma here, is the group that defines the surface, as that the points are at most r distance from each other. Then there's sub-exponential growth for these bounds for any r less than rx. It's a bit like a technical condition, but basically it just means it counts the number of like short loops inside the surface. That what are the number of closed loops that you have inside the surface that you have here. And this quantity, you can choose these Rx and Cx. So there always exists some Rx and Cx. Actually, you can actually the one Rx that you can always choose here is injectivity radius. That's an example which satisfies this, with Cx equals to 1 actually at that point. That's always true. if you choose the injectivity radius of the surface, then this is always true. But the caveat here is that if you choose the Rx to be injectivity radius, it's not very good estimate. Actually, you don't get very effective estimates that you want. So the better Rx you choose, the better estimate you get for the L infinity nodes. But basically, this is like a technical condition that you get an upper bound like this. You get the Cx that's in the front here on this part, and then you get the Rx division on here. So we proved this using some basic harmonic analysis ideas on hyperbolic surfaces to get into to this type of estimate. Like this Selbert transform, for example. But when you do this, you can then choose with the right number. So here I'm using Rx to be C log the genus for some constant C, and big C I'm using 1 over the injectivity radius. With these numbers, we can prove this kind of a random result. So for random surface, for all eigenvalues, at least 1 over 4, the L infinity norm is bounded from above by some constant in the front that depends on eigenvalue, divided by 1 over the injectivity radius square root of that times the log of the genus. And this happens with probability going to 1 as genus goes to infinity. Of course, we can always get a rate for this probability growth as well. I'm just not writing it now down. Okay, so how is this compared to all the previous results? So that's kind of the main thing. So remember, this is kind of like now the conjecture that I would expect to be true. So if you remember the Bauer-Schmidt Knowles-Yau result, they had this square root of n. I'm just rewriting it again, the kind of a theorem that they had. This was in the previous slide in the beginning. And then I define this conjecture that for a random surface, for all eigenvalues, at least 1 over 4, and if you have an epsilon positive, then this is what I would expect maybe to like compare to their result. That it's to the square root of the volume. And in the previous slide, we got something like this, but we had the square root of the injective radius times the log of the genus. But the problem with that is that that's log of the genus is not giving it. Basically, you would need to have genus there without the logarithm. So there needs to be some other idea that we need to use to be able to improve what we proved before to get into this quantum unique ergodicity type of situation. So that's what we are currently doing. We are trying to like explore their ideas. So they have some very interesting probabilistic ideas that we are like trying to adapt into the surface world, into the Weil-Petersson model, or possibly some other probability model to maybe get into this conjecture that would be the natural analog of the right bound. And the other thing that we would be interesting to see is the degree that they have here. What does this mean for surfaces, for example? What does it mean, the degree to grow for a surface? I am not sure. I think what they remarked in their paper, that it was more like a technical condition. It's to do with their method of the proof that happens using this something called local switchings that they are using in their random graph proof. But with here, I'm not sure like what would it mean. We have this kind of like an idea maybe that it could be related to the eigenvalue actually, because on a graphs you can define a Fourier transform operator, this kind of semi-classical Fourier transform operator, and if the degree appears in that operator. So if the degree grows, it has more and more like oscillations going on inside. So it's a bit like a semi-classical Fourier transform when the degree is growing as well as the n. And that's why I was maybe guessing that maybe there's a hybrid bound that combines this, that makes this effective, that you use the semi-classical analysis, maybe some mixing of the geodesic flow, for example, to enable a bit better bounds from the large eigenvalue and combine these into some kind of a hybrid estimate, which would be going into this. And that's how I see at the moment, maybe how would you be able to approach the original quantum unique ergodicity problems, that you need to somehow understand maybe like if you can do something with this, these bound first with maybe a hybrid estimate or something. I think this is like people have tried this before. I think this has been like, people have tried to randomize the surface and try to prove this quantum unique ergodicity, but I don't think this is hasn't resulted in any like advances yet. So our idea is just to use the graphs first and see what's the analog of the random graph situation in the surfaces, and then maybe work our way from there.
Sorry, let me ask you a question. So could you remind me what the role of the epsilon is in this conjecture?
This epsilon is just to have control this how much fluctuation there would be here. So basically here is there's no epsilon. In some sense the epsilon alpha epsilon is 2. Like maybe it's 2, maybe it's just a constant function 2, but I'm just assuming that maybe there's some kind of a epsilon dependence with the upper bound for this. Like that's why I'm kind of guessing. Actually, this kind of, yeah, I think that's kind of the idea. That there's some fluctuation coming from the error terms that come into the proof, that this should be true in this form. That's what I'm guessing. I've been talking to a couple of other people as well, like what they think, but let me know what you think about this, if this maybe would be a valid way to conjecture. I have some time left, I guess, to maybe a little bit, yeah?
Yes, say 10, 15 minutes.
Okay, yeah, so this is kind of the main part of the talk, of the kind of the results, but then maybe I can go a little bit into the proofs. So let's go to the proof structure of the L infinity bound, which is kind of the newest one that we've done. And I'll talk about this NR to be the maximum number of primitive geodesic loops of length R passing through a point in X. It's a topological, that is a geometric notion that we define is counting this number of primitive geodesic loops. So these are related to the assumption of what I had before. And then I have this short loop condition that supposes that for any Rx, that there exists this Rx and Cx, as for any R less than Rx and delta, there is this bound with some C delta. I should have here that there exists some C delta positive with this property. So this was exactly the condition we had before. I'm just using a different way of writing the supremum over all the pairs of points in the fundamental domain, using just a topological idea of like a number of primitive geodesic loops of less than R. And if you use this condition, then this is what we proved. This is what we had the kind of proof over here. So as I mentioned, like before, I will go into how do you prove, kind of get that bound in a second. But let's say we get this bound, but then there is a problem with this bound to get to the random theorem that I had, is that we need some kind of effective version of a result of Mirzakhani and Petri, and prove this kind of a result that this Rx is at most the C log of the surface volume, which is the basically genus, to get this estimate into the random version. So basically, this is the structure of the proof. We first prove this kind of a spectral estimate, and then we use this prove this kind of geometric estimate. So this is where the random surfaces are being used, the second one. And we couldn't use Mirzakhani's original work directly because, as I said, okay, you could get the result that we wanted. So let me actually just show you very briefly the result, the random theorem. So this is what we are aiming to get, log of the genus and injective radius here. But we couldn't get this kind of an estimate because random surfaces don't have the injective radius growing like log genus, basically, at the infinity. Actually, you can prove the expectation is like some finite number. So as I said, this short loop condition is satisfied with this Rx is equal to injective radius and Cx equals 1. And I'll show this how this side goes. But Mirzakhani had proved, as I mentioned, that this is uniformly bounded. So you can't really use her results directly to get to this stage, to get to what we were hoping for. So that's why we needed to slightly expand our ideas, what Mirzakhani and Petri did in their work, to be able to get this kind of estimate on the other side. So let me show the idea of the proof. So this is more like now goes into more analysis. So this is pure analysis. Let me prove this bound. Just like a very classical standard argument using something called Selbert pre-trace formula. So let's take this eigenfunction, the Laplacian, and take its L infinity norm, and we want to bound it like this. but I'm saying that this is not a good bound, but it gives you the basic idea how do you get the better bound what we have for the short loops. And so we take a L2 normalized eigenfunction, and we assume that, okay, this is with the eigenvalue lambda square. Let's just assume that it's of this form lambda squared, happens to be like, let's just write for convenience. And let's define R to be this Rx that was in the theorem. And the Rx now is the injectivity radius. So I'm basically assuming that this Rx is the injectivity radius, and then I'm getting this 1 over the injectivity radius here. And then I take a smooth, rapidly decaying function with the Fourier transform supported in a compact interval, such that the height of the function at 0 is almost this injectivity radius. So we localize in the spectrum around an eigenvalue actually here, such that the function is like basically of height the injectivity radius. And what we can do then with that kind of a modifier or smooth function, we can plug that into the Selbert pretrace formula. This is a kind of like a way to connect the Laplacian spectrum into the length spectrum of the surface, studying these loops. It's a very important connection. It's always very good to exploit. If you want to use random surfaces, randomized topological ideas, then you can translate into spectral ideas using this formula. It's kind of the first thing maybe pops into your mind if you look into this theory. So you take this Selbert pretrace formula to use this as a test function. So this is like over the eigenfunction, this is like a trace formula. And the right hand side, you have the main term, involves this. I don't know if you've seen the trace formula, you have this kind of tan H terms coming out. And then you have the sum over the rest, over the loops, kind of basically. These are like the group elements which correspond to basically the kind of geodesic, primitive geodesic elements that we have in the surface. And then we have, okay, I'm using this radial current. This is kind of something of the, like I said, you get the Selbert transform out of this. So that's kind of, that comes out of the remainder. This is the kind of a theorem test that you take any test function, then you have to kind of compute this kind of like a Fourier transform in this sense with using this kind of function. But then using just this basic property that this kernel is supported to minus R to R by using the definition of this function by being like kind of localized around the spectrum, we know that this sum is 0 because this injectivity radius is the bound for this. Remember, R is the injectivity radius. So the loops you can never get too far over the injectivity radius. So there's no points that are mapped outside in here. You're staying basically inside the whole point of the wall. This kernel is basically 0 when you have jumped beyond the injectivity radius. It's this idea of that you don't propagate beyond the injectivity radius, basically, the waves that you have here. And then you get this bound. Just from this formula, you get the main term here, and then you have the remainder, which is coming from this decay, the rapid decay that you have in the Fourier transform support. So you get this tan H S, and then dividing by R, you get the estimate we wanted. Because R is the injectivity radius, we're bounding the L infinity norm at the point Z. Because this is a pointwise estimate, this Selbert pretrace formula, so you can do it at every point Z in the fundamental domain. So basically you get an upper bound for the L infinity norms of any eigenfunction from this formula. And we use the same idea in the more general theorem. You just need to kind of do this a bit more complicatedly. You have to kind of use a different propagator. So we have to, like, the way this works is this finite speed of propagation that is only non-zero outside this interval. And what we do in our proof, we replace this by a propagator of this type, which has better properties. And it was used by Ivaniech and Sarnak in their bound for the L infinity norms of eigenfunctions on arithmetic surfaces. So we used kind of similar idea that Ivaniech and Sarnak did in their work to kind of get the same bound. And now then we can use the random surfaces better. Okay, so that's kind of the analysis side. There's a little bit like we can do some LP norms as well, like, by the way, if someone wants to know about the different LP estimates, we just need to use some kind of a TT star argument at that point to make that happen, which makes it quite technical, but it's still possible. And then the random surfaces, this is kind of like the side that we wanted to do. So the other side, that we basically have this geometric condition that we want to have certain bound properties from above. So basically we define this kind of a set AC of genus G surfaces with the property that there exists there exists a point X in the surface such that there are at least two primitive geodesic loops gamma in X of length at most C log G passing through this point. And what we need to prove is this property for this, because this implies that actually this short loop condition is satisfied then with actually just we can get the trivial bound for that by bounding the number by 1, because there's only one loop. Like if you prove that the complement decays, then like this AC is kind of the complement of the short loop condition decays, then you get that this is just basically one loop. So that's sub-exponential growth. That's how we do it. And I'll just give you a very quick idea of the simple geodesic case, where I'm assuming that these are, so let's pick a point in the set and pick two such loops that we had in the set AC. So this was the set AC. We can pick two loops. There's at least two primitive geodesic loops. Let's assume that they are simple. So there is basically some topological reasons to assume the simple, because there's a lot of like self-intersections, and this causes more complications in the whole theory of Mirzakhani. But let's assume that they are simple loops, then we get much simpler. We can draw a picture then. So what we do here is that we take these two loops, this is the surface here, let's say, that's on the left-hand side. These are two possible examples how the loops could be, for example. This is like an example of the topological surface that defines the genus. And we draw the loops that they intersect at some point X, that's some point X. And what we do is that we take the regular neighborhood of these two loops, and then homotopically expand them into these geodesics. So we have these two geodesic points over here. So this would be, if this would have a metric structure, we think about the homotopically to the ones that are at the shortest geodesic, and then we cut at these points the surface. So we create another surface that depends, it has some genus or some number of boundary components. So this kind of has 4 in this case, and genus is 0 in this picture. But on the right-hand side, we have some other way of doing this with the loops going like this, and then we can do the same kind of a procedure. But basically what you want to do then, that this what remains here has some maybe small probability, that the probability of this kind of surface existing is very small. So that the original property of the surface has a very small probability. That's what we wanted to prove. We wanted to prove the probability of this set has small. So what we end up doing is bounding the number of surfaces with, let's say, this number of boundary components with certain properties. That's what we end up kind of doing. And everything boils down to Markov's inequality, which is we have this kind of we identify that property of the surface having this kind of number of boundary components like this, and let's say being some property, and we use this kind of Markov's inequality. We think about this as a property of a surface, like an observable in the space of all surfaces, which have certain property that, let's say, there are like certain number of boundary components, and that's at least T, for example. And then we can bound this by this integral over the surface, using the Weil-Petersson volume. And the reason we want to do this is because Mirzakhani has a very nice kind of integration formulae to deal with these types of integrals. I think this is like, I ran out of time, but let me give you the kind of basic moduli space notations. This would be like the surface we cut out, genus G, in boundary components, for example, and then we have this Teichmüller space that defines with certain lengths for the boundaries, and we have the mapping class group that defines the kind of topological actions in the surface, and then we have this moduli space and the compact case given like this, and then the final slide is this. I want to leave this here in case someone watches the video, they want to pause the video and just read the slide. So basically, you can then use this Mirzakhani's integration formula and some volume estimates for the Weil-Petersson volume to actually bound the existence of such a subsurface conversion to 0 at infinity. So that's how all these comes together. That's all I wanted to say today. Thanks.
very much. So I'm clapping live, people are clapping virtually. So any questions for Tuomas?
Could I ask about the bit where you say that, I mean, this was all kind of, you were presenting this at quite a high level. You said at some point you used Markov's inequality in which you had some parameter t.
Yeah.
I mean, Markov's inequality is quite a blunt inequality. Presumably you have to make a very cunning choice of t when you use it.
Yeah, here I think the t is basically, let's look at this function. This is the function I'm using, this f gamma. So I'm just want it to be like basically multi-curve that the length is at most. So it's at least actually the t is, I think I'm using basically any like half, for example, I think I'm using because then this is an indicator function being bigger than something. That's how I'm using. I'm basically applying for the indicator function, and whether the indicator function satisfies the property, it says that it's positive. So let's use some c maybe that depends on the t is some constant which is just positive then. But yeah, I think that could be improved. Like there's a lot of steps in the proof where I'm thinking we are doing like the worst possible estimate. It's like the naivest part of the thing, and so it's like I think there are many places where I feel like using some higher order moments, you could get much better things going on. We were just desperate to get into the integration formula somehow, so that's always the...
Any more questions?
Can I ask a question?
Sure, go ahead.
In your estimates, you had an implicit constant which depended on the eigenvalue parameter lambda.
Yeah.
And you said lambda is bigger than a quarter or something like that.
Yeah.
But can you say something when lambda tends to infinity, like in the classical?
Yeah, you can actually. It's possible in that situation to say something, but then the problem is that the estimates we have are very bad. We are like completely ignoring the lambda estimates. But if you go to the literature about semi-classical analysis, like Hermander's estimates, like their books, and start to open these books and you start to think about the quantization they do, and Egorow's theorem and these notions, and you are trying to think, how does this estimate depend on the geometry of the surface? And they have completely ignored the volume. There's a constant that depends on the surface. And it's an absolutely horrible constant. And it's like, it's this kind of an estimate they have, which is, in our case, we are doing the same. We are like ignoring the lambda. So I think the possibility in the future is to put them together. So maybe propagate the waves beyond the injectivity radius to get some cancellations from the mixing of the geodesic flow using quantization and Egorow's theorem. And at the same time, do this, what we are doing, this kind of flattening that we are doing with zooming out at the same time. Maybe you get much better estimates by combining these two estimates that you get.
Would you have to assume, in this case, would you have to assume some relation between G and lambda?
Yeah, I think I would assume that, let's take an interval that's, let's say, length is from 1/4 to genus, for example.
Okay. Mm-hmm.
Maybe like the lambda is roughly of the order genus, or maybe log genus or something like this. I'm not exactly sure what's the best. Maybe the genus is the best because that's like the volume. And then let it grow at the same time. Then maybe you have to split the interval into two parts, like the initial part where you use our estimates and the end part where you use high frequency estimates like the semi-classical methods.
Thank you very much.
Any more questions, comments, remarks? Okay, if not, let's thank Tuomas again for the very nice talk.